Hello, my name is Baylee Kinkade and I'm a graduate student at Eastern Michigan University. Welcome to my presentation about modeling solar weather with neural networks. Here we have an artistic representation of a geomagnetic storm, otherwise known as a solar storm. We can see how the Earth's magnetic field in blue is interacting with the charged particles emitted from the sun. On one hand, this causes the gorgeous aurora we see at the poles, but on the other hand, it can damage the satellites in our atmosphere, cause electrical grid issues, and otherwise wreak havoc on our modern technology. The goal of my summer research project was to develop a neural network to model solar weather so we can protect ourselves from its destructive effects in the future. I used DST values for the model. The reason I did that is because DST, or Disturbance Storm Time, is used as an indicator of the intensity of solar storms. It is measured in nanoteslas. The first approach I used was categorical. The classic example of a categorical neural network is one that interprets whether a picture is a cat or a dog. One tried and true method of modeling DST is to use the Burton equation. I had hoped to be able to categorize DST values using inputs such as the velocity of the solar wind and the value of the interplanetary magnetic field in a way similar to how an equation works with multiple inputs. However, this approach failed badly. I had an accuracy of about 0. Really, there were two main issues with the categorical approach. For one, the network only counted itself correct when it predicted the exact DST value as the actual data. Say DST was 8 nanoteslas, but it predicted 9 nanoteslas. Even though the value was really close, it didn't count towards the accuracy of the model. The other issue was that, in reality, previous DST values will absolutely help predict future ones, and this type of model evaluated each point individually. So the solution to this was to switch to a recurrent neural network with long short-term memory cells, which are able to factor in current and prior data to make a prediction. This is the first recurrent model. I used 500 LSTM cells and 3 layers of dense neurons in decreasing quantities to process the data. The blue line in the graph is the actual data, the orange line is the training predictions, and the green is the testing predictions. It follows the general pattern of the data pretty well, but when there is a larger storm, you can see this when the graph sharply dips into the negative values. The model predicts a large spike, but it still underestimates just how big that spike is. For Model 2, instead of 1 year of daily average DST data, I used 5 years. This cut the testing root mean square error by about 50%, so more data is definitely useful, but you can still see the problem that it has with underestimating the full intensity of the storms. For Models 1 and 2, I used daily average DST, but I began to wonder how the model would work with hourly average DST data instead. For the hourly model, I decreased the amount of LSTM cells and dense layers, decreased the amount of data used to train the model, added dropout to sort the data, and changed the model's optimizer function from atom to root mean squared. The hourly data does seem to help the accuracy of the predictions, but this particular data set lacks an extreme solar storm. So it does have an advantage there, but the testing root mean squared error of 3.72 nanoteslas is still respectable considering the scale of the data. For Model 4, I reduced the training data again, decreased the dropout, and increased the number of LSTM cells. I was hoping this would help the slight overfit. It lowered the root mean squared error for training and testing, but the overfit is still present. I also tried the previous model on 5 years of data like Model 2 had, but it didn't significantly impact the results. Before I conclude, I want to thank Dr. Kinkade for being my advisor for this project and also helping me in many ways throughout my time at Eastern. I also want to thank Dr. Kalin for encouraging me to explore the world of artificial intelligence. His machine learning class was also vital in providing me with the knowledge and techniques I used in building my neural network. Finally, I wanted to thank the Michigan Space Grant Consortium board members for selecting me for the graduate fellowship, which allowed me to pursue this project. Here are my references. Thank you for listening to my presentation. I hope you found it enjoyable and exciting.